Okay, hello everybody. Welcome to another summer CFPU seminar. We're taking advantage of the virtual setting and it's my pleasure to introduce today Michael Kopp as our speaker. I know Michael since my undergrad days at the University of Cyprus. We worked on large-scale structure formation together, and he was pivotal on my journey further in physics. He then moved to the Institute of Physics at the Czech Academy of Sciences in Prague. And the last year, he's relocated in Stockholm at the Nordita Institute for Theoretical Physics. From where he's going to tell us about his recent work on generalized dark matter and possible implications of the H-naught problem. The stage is yours, Michael.
My mic is still on, I guess, yes. Thanks a lot for having me. And before I start, I would also like to encourage you to just ask immediately if anything is unclear or if you have a question, because now I have the super large lack of feedback and I don't want to bore or even anger anyone with being incomprehensible. So please just ask right ahead.
If you do anger us, you have the advantage of being out of our reach.
That's good. I might not even notice if you leave, if you get angry. So that's also good for me psychologically. All right. So this project has been going for a very long time. It started when I came to Cyprus as my first postdoc, and I was working with Konstantinos Gordis for the past 5 years on which this ERC run. So so this whole bunch of papers all cover this same subject that was part of Konstantinos' ERC project, and we two also collaborated with various other postdocs that were around during the time. Katerina Markovic actually was never a postdoc of Konstantinos, but we nevertheless collaborated with her on one of these papers. So what it is about, it's about testing the cold dark matter paradigm. So CDM is cold dark matter. And we do this by parameterizing the possible properties of dark matter in a very general way and see how they are constrained through cosmic history by using the CMB, mostly the CMB. We also include some other data sets in combination with the CMB, but we mostly rely on the CMB because it is so well understood and free of systematics that we are less likely to confuse, say, astrophysical or complicated nonlinear or baryonic physics with properties of dark matter, which go beyond the CDM paradigm. And there's also recently, when we put out our last paper, we released also 2 codes. One is a modification of class that you can use immediately and which contains all the relevant pieces that we used to write this final paper, including also as another separate code, the MCMC sampler that we used. That was actually written by Stefan Illich. And it's super easy to use, and it can handle an enormous amount of parameters in a way that is quite intuitive and manageable compared to MontyPython, which we started with. All right, so you can go ahead and get your hands on everything if you want to. This is a quick outline. So I first give you some motivation of why we want to do this whole thing, why to look for properties beyond CDM. And then I'll introduce you to this generalized dark matter model, which is for the rest of the, on the rest of the slides, usually denoted by GDM, or even shorter, just by little g if it is a subscript somewhere. And what this model does is it introduces 3 new parameters, or rather parametric functions, 2 for the pressure of dark matter and 1 for its viscosity. And then I will tell you what how the CMB is affected by these new parameters and what we get for the constraints mostly coming from the Planck data of the cosmic microwave background. And we have done this step by step. So we started initially with assuming that these parameters are constant. Then we assumed that one of them, the simplest, has a quite generic time dependence and set the other two to 0. And then the last case, which is the most recent one, where we allowed all these parameters to be freely time dependent. And that's where we, for the first time, actually found some surprises, because previously in this first and second case, we always found that everything was consistent with LambdaCDM, or in other words, that LambdaCDM was contained within the error bars of these parameters that we constrained. I forgot to mention that these 3 parameters reduce to CDM if they are all 0. So the LambdaCDM model is a part of this generic model. And now these new results indicate that there might be actually some physics beyond CDM. And very interestingly, and also unexpected to us, it seems to be related to the H0 tension. All right. Now for the motivation. Why testing the cold dark matter paradigm? It seems that we usually don't even think about playing with that. There's much more literature on changing the cosmological constant to something more generic, rather than the CDM part of the concordance model. And the reason is that there's plenty of extensions of the standard model of particle physics that are extremely natural looking by themselves, and they all more or less are described by this CDM. So there's axions, WIMPs, stereo neutrinos. They are natural extensions and they look like CDM. And the second part is because all our data that we have, which is all gravitational in nature, indicates that the CDM paradigm is in conjunction with general relativity fitting all of these observations. So there's no reason really in the first place to start modifying the CDM component of your model. However, there is of course the small scale tensions with the CDM model, but they might be just reflecting our ignorance or not total knowledge of baryonic or nonlinear effects. So it's not clear if this is an indication that the CDM model needs revision. And so that's why we also focus mostly on the cosmic microwave background, because it is so clean, because it involves only linear perturbation theory and baryonic physics that is extremely well understood. There's also no reason really to think much about modified gravity when it comes to replacing cold dark matter. There's no theory yet that would actually do the job. So therefore, the most, I would say, uncontroversial thing to try is to go into the Einstein equations and replace the energy momentum tensor for cold dark matter by this generalized dark matter fluid with subscript G. And
Michael, sorry, can I interrupt and ask a question?
Of course, yes, please.
Yeah. So I'm curious why you only talk about cold dark matter and geometry when like the lambda is sitting right there, and I guess it's also one of those big problems,
Right.
cosmologically speaking. So I wonder if you had something to say.
Yeah, it's an admittedly arbitrary choice to now leave lambda completely as is and only try to see what happens if you play around with the CDM part of your total energy momentum tensor. There's of course also very specific models that try to combine the physics of the cosmological constant and that of cold dark matter into one unit, but I don't think they are successful. And now if you are allowing both of these ingredients to be independent, then you open so much freedom that it's, at least it seemed to us, unlikely to be helpful in getting any handle on the dark matter properties, because they might be so degenerate with the properties of the cosmological or the extension of the cosmological constant.
Yeah, that's very clear. Thank you.
Okay, right. So now that I tried to motivate why one should look at this generalized dark matter. I actually have to tell you what this generalized dark matter is, because in principle it can be anything. And so we have to, it has to go in some physics intuition in constructing your deviation from cold dark matter. So let's start with actually looking at the energy momentum tensor for cold dark matter. Usually one defines or approximates cold dark matter with a pressureless perfect fluid. Especially in CMB codes like CMB or class, there's that is the standard. There's no need to model the cold dark matter, say with the Boltzmann equation, which would be a more correct way of doing things. But in the case where linear perturbation theory applies, this pressureless perfect fluid is completely equivalent with the collisionless Boltzmann equation. So that's fine. It's also interesting to ask, what do we actually know about this energy momentum tensor once we plug it into class and constrain it with the CMB? We actually get only two numbers. One is the abundance of dark matter. Here this little omega is the abundance or the energy density of cold dark matter in some funny units. You don't have to really know what these units are, but it's important to know that we have constrained this parameter to percent level. Or not we, I mean we as the cosmology community. And the other number is the contribution to the isocurvature initial conditions that can arise from cold dark matter in principle. Simple inflation theories don't predict any isocurvature mode, so you would expect this number to be 0, but you can, in principle, go ahead and constrain this number that involves certain model assumptions, but nevertheless we can constrain certain aspects of the initial conditions of how the clustering of dark matter started out very early in the universe. So it's just two numbers and that's it. We don't know anything else about cold dark matter if we only rely on this energy momentum tensor. Now it gets much more interesting if you extend this energy momentum tensor to contain pressure, which generically can be a function of anything. That's why it's super arbitrary in principle. Similarly, for the shear, that can also just be a function of anything. And so what this just tells you is that in principle, there's more dark matter properties and we can potentially measure them if we somehow parameterize smartly what is shear and the pressure in this most generic energy momentum tensor is. And for the experts, I will now tell you a little bit of the details. If you don't care, you can. I will tell you when it's over the slide, and I will go back to the more understandable, less formula heavy part. So for linear perturbations, we know that this part is uniquely described by the conservation equation, which any energy momentum tensor usually satisfies. And you get evolution equation for the density perturbation and for the velocity perturbation. Now, you have two equations for density and velocity perturbation. And that in principle tells you everything about this part of the energy momentum tensor if this thing wasn't present. So that's why CDM is basically uniquely defined just by conservation of energy momentum. Now for the pressure, you can, at linear perturbation theory, introduce two functions to parameterize what it can do. The background equation of state W and the pressure perturbation, which is the perturbation of the pressure around the background. And for convenience, we divide it by the energy density. Now, there's now an infinite amount of freedom already to parameterize these two functions. So we have the background equation of state, which is in principle an arbitrary function of time. And we have the sound speed, which is related to the pressure perturbation by the following ansatz. That's not the most generic pressure you can write down, but it's a very natural one. So it consists of a part that is called the adiabatic pressure and a part that is called the non-adiabatic pressure, which is this whole expression. And the non-adiabatic pressure vanishes whenever the sound speed equals the adiabatic sound speed, which is defined up here. So the adiabatic sound speed is just determined by W and its time derivative, so it's fixed, you cannot change this. So if you want to change the perturbative pressure in any way that is not equal to CA squared, you have to do something to this very simple expression that you usually assume. And this is a very natural thing you can do to it. You have this part that vanishes in the case of adiabatic pressure being proportional to the density in the rest frame of the fluid. That's something that...
Michael, sorry, this is
Yes.
Manuel. I have a question. I thought this was actually very general. Is there a case in which this expression, this decomposition of capital pi does not apply?
Right, there's plenty actually. And so in a paper I will come to later, I try to work out which cases actually have a pressure of this form. And it's not very generic. If you have a single scalar field, it satisfies this. But there's rarely a scenario in which it is just this. It's a very good approximation in some cases, and it's also, it has nice properties from a phenomenological point of view. The reason is that if you would write down any other kind of gauge invariant, so this is a gauge invariant density perturbation. It needs to be gauge invariant because the non-adiabatic pressure is gauge invariant. But there's an infinite amount of gauge invariant density perturbation. You could think of the Newtonian gauge density perturbation here, and it would produce very strange behavior on super horizon scales. So actually, if the sound speed is non-adiabatic. So actually only this rest frame density perturbation has the nice property of not inducing evolution on super horizon scales whenever CS is not equals to CA. So it has some nice properties, but actually not all physical models fall into this.
I see. All right. Thank you.
And the final ingredient is the shear. And we are interested only in scalar perturbation, so the scalar part of the shear here. And again, Wayne Hu just postulated this equation, and you might ask why this equation and not why an equation of motion, why not an algebraic equation like for the pressure? This was actually something I forgot to mention. In general, you would expect this pressure to be to satisfy some evolution equation and not being algebraically related to the density. So that's also what I found for certain special cases. And here we have a time evolution equation rather than just, rather than just the sigma being proportional to something. But I experimented with this a bit, and it doesn't really matter much if one replaces the time derivative here with an algebraic shear. It has very similar properties, but still there's some freedom in what you write down. This is motivated, even though this paper came much later, by the observation that for neutrinos, when they are becoming non-relativistic, if they are massive and free stream on small scales, they approximately satisfy this equation. So there's a nice physical reason for this equation. You can imagine that that the Boltzmann equation that you in principle would have to solve to all orders in the moments. This is just the second moment of the Boltzmann equation. You can actually truncate this infinite hierarchy of moments approximately if you write down this specific equation for the shear. So it has a nice physics origin for the very special case of freely streaming massive particles. But of course, that's not a justification to use it in general. And for freely streaming massive particles, this viscosity is determined dynamically. And here we assume it's a free parameter. And in principle, you can imagine that both sound speed and viscosity are functions of time, tau, and scale k, so in Fourier space. Here, that's why there's k's. It's it's in principle impossible to constrain these functions in most generality, because any crazy behavior in space and time could induce arbitrary effects. So you have to be very sophisticated in coming up with smart versions. These functions can actually depend on scale and time so that you capture interesting physics. For instance, if you have an oscillating scalar field like an axion, an ultralight axion, people consider as an alternative to cold dark matter, then the sound speed is actually proportional to k squared. So it's not k independent as for a perfect or imperfect, normal imperfect fluids. So there's in principle already plenty of physics contained in these functions. But there might definitely be scenarios that don't fit into this strict template. I mean, it's not very strict, that's why it's called generalized, but it's still in some sense strict. And so our results need to be understood as always referring to the space model, and you cannot just arbitrarily apply it to your model if your model doesn't approximately satisfy these relations. All right, now what have we actually done in the most recent paper? We have binned, so we have first of all excluded the k dependence completely and only allowed these parameters to depend on time. So we allowed the W, the sound speed, and the viscosity to depend on time in this very specific way. So imagine you have here the scale factor starting in principle as early as you want when your Boltzmann solver starts until a equals 1, redshift 0. And we divided this whole range into 8 or 9 bins and allowed each parameter W, Cs squared, and Cvis squared, the viscosity parameter, to be free in all of these bins. With the only restriction that W was forced to have a wider bin in the last bin because it's degenerate with the cosmological constant there. So we had to make it wider for W, but otherwise it means that we have 26 parameters in addition or on top on the normal LambdaCDM model, which required a very sophisticated Monte Carlo scheme to actually track the behavior of our chains in real time so that we are not wasting time too much, and also to know when stuff has converged. And so this is something that Stefan put together. It's based on MCE, and it also links the Planck likelihood to class. So it's very convenient for anyone working with the CMB, and you can just use it. It should work out of the box. And if not, you can contact me or Stefan. The data sets, we used the 2015 Planck data. We are currently working on what happens if we include the more up-to-date 2018 data. There's actually very surprising and interesting stuff showing up, but I won't tell you about it because it's not done yet. And but apart from this Planck TEB spectra, we also use the Planck lensing power spectrum and the collection of BAO data for the sound horizon that is extracted from large-scale structure surveys, and also as a sort of test, the HST Hubble H0 prior on the Hubble constant. So we don't combine them because they are not consistent, but sometimes we combine HST with the Planck stuff and sometimes BAO with the Planck stuff to see how much we improve our constraints.
Michael, one question.
Sure.
Have you why this specific bin? Have you tested on sensitivities if you've been otherwise?
We tested a finer binding even, and that would never converge. And we tested, of course, also a wider, fewer bins that are wider, and they would produce similar looking results. But if you make them too wide, then you might force something on the dynamics of the background or perturbations by imposing it to be constant for a too long time. So we just found for practical reasons that this binning was best suited for us. But in principle, there's of course, why do we have them equally spaced in log A rather than have them equally spaced in A or any other kind of natural looking spacing? We haven't really explored that. So, and we also didn't want really to induce any kind of priors. In some sense, it's a prior because we are weighing these spins according to the log A for their importance. And maybe it would have been better to weigh them according to conformal time bins. So it's not clear. But so this is just what we did, and we haven't tested very different looking bins. So we don't know.
Thank you.
So this is the first surprise that came out from our most recent investigation, in which we allowed all these parameters to be as free as I've just explained it to you. And what you see here is constraints on the abundance of dark matter. Here, the background density of dark matter, GDM, the little g stands for GDM, scaled by A�3. The reason why this A�3 is here because for CDM, you would expect this number to be constant in time. And that's why the arrow bar that you see here, so this gray bar here is actually the arrow bar on this quantity, as you will find it from the LambdaCDM model and these data sets. So of course it doesn't change in time because it's constant by definition. But what is interesting now, if you contrast this with the constraints that we get for this very generic GDM model that has 26 more parameters in it. And you see there's a time early on where these contours barely overlap. So the yellow and gray contours are 3 sigma. And here, of course, they do overlap, but there's also times where they don't overlap at all. And this is for a very extended period in time. So it seems like, and here I indicated for you the time of recombination and matter radiation equality. So it seems like that the data wants this abundance of dark matter to be higher early on. And then later on it is again, even though of course the error bars are very wide, at least it's still consistent. It's again consistent with the CDM error bar. So this was...
Sorry, Michael. I find really interesting that before 10 to the minus 4 right around equality, it seems like this thing is like decaying with A, which it seems to be a behavior like radiation or even something weirder. Do you know what value of W you're getting here? Or incidentally, what's the power of A cubic times rho?
I will show you in a minute a similar plot that shows you the constraints on W itself. So this is a derived constraint.
Of course, yeah.
Sorry to interrupt. Yeah, I probably have a follow-up question. Just you show that for the region you zoom in, that you also see the overlap, but then it's like it's generalized dark matter also prefer like slightly higher values. So I assume you will also show us what kind of WCS squared that's like and viscosity, C viscosity squared and corresponds to.
Right, I will. So this is sort of the teaser I'm currently showing you, and I will. Okay. And I will get back. I already spent a lot of time here, but I promise I will get back to the details. So the thing is, it's difficult to plot all these parameters because there's 26 of them. But I will show you some plots that show you the relevant pieces that explain what we find here. Hopefully.
Okay, thanks.
All right, so this was sort of the first surprise, and the reason why it was a surprise is because all our previous studies always were sort of perfectly consistent here in this range as well. So the arrow bars were of course wide, but everything was always consistent with LambdaCDM. LambdaCDM was always nested in the arrow bars of our GDM model. So this is the first time it didn't happen, and we didn't really expect it because we had some intuition that turned out to be not quite right about the possibility of correlations between the equation of state and the sound speed. So in the case where you are in a GDM dominated universe that is well after equality, there's actually no correlation or physical connection between the background equation of state and the sound speed. That is precisely why Wayne Hu decided to come up with a specific form for the pressure. But it turns out that very early on, when you have radiation domination, there is a degeneracy between the equation of state and the sound speed. And that is precisely the reason for the offset that we find here, which drives this whole physics to be as we observe it, to have the dark matter larger early on. And I will get back to this in a minute, or in a few minutes. Then the second kind of surprise, which of course is connected to what I've just shown you, is maybe even two surprises here, but this one was expected really, that if you allow the sound speed to be non-zero in all these bins, they just bias your sigma 8 to be smaller values, because sound speeds and viscosities can only cause the decay of the potential, or in other words, a slower growth for the dark matter perturbations. And so imposing this constraints, which is of course physical, that the sound speed and viscosity need to be positive, you automatically bias your contours. So here I show you sigma 8 clustering at redshift 0 and the abundance of dark matter from LambdaCDM to the scenario where we have only W free in these 8 bins and set the sound speed to 0, to the case here in these color-coded dots when we allow them to be all free. So sound speed and viscosity, if you give them so much freedom to be positive throughout the history of the universe, they will just bias your sigma 8 to smaller values. And here the color code is the present day value of the equation of state. Maybe more interesting and also more unexpected to us was the biasing of Hubble, the Hubble constant. So again, I show you here in the gray contour, which is tiny here, the LambdaCDM. And the blue contour here is the case where we only allow W to be non-zero in these 8 bins and set the sound speed to 0. So even though it's now a much larger volume and parameter space, we had previously that LambdaCDM was perfectly sort of expected in this contour, but now there's this kind of bias towards larger values. So you see that the contour is sort of emptied out here and everything has moved up a little bit. And this is related to the density of dark matter to be favored higher pre-recombination. And I will get back to this later. So this was sort of the upshot of our findings, and now I will go into more details and also tell you a bit more about the physical meaning of these parameters. I can't really go into all the details, but maybe this is really illuminating a very specific example in which all these 3 parameters are approximately equal to each other. You would expect such a relation in the case where dark matter is just freely streaming particles. And this blue contour here is the constraint that we get if we impose this condition on these parameters, that they are all equal to each other. And now you can compare this to other constraints or expectations. So for instance, here I show you the constraint that was obtained by assuming warm dark matter, which has a very specific scaling in time, a 1/a² scaling. So this is this 1 plus z² here. So this is redshift, and this is the magnitude of these quantities. And you see that, of course, at redshift 0, it's tiny because you've just extrapolated it from early on. And another interesting example is the case of CDM, when you model it more accurately, not by a pressureless perfect fluid, but you take into account that nonlinearities back react on the linear physics and even the background and modify the dynamics slightly. And there you would expect this black dotted line. And you see that it's having an opposite behavior as what you would expect for warm dark matter. And of course, what you would expect for a really physical system is that it's sort of some combination of both. Any kind of particle, or most of them, are created somewhat warm, and so they will always behave like this, and then they would go up again, these parameters, due to nonlinear structure formation. Of course, the scale will shift depending on your model, but this is at least what you would expect in principle to happen. And so you see that there's the potential to maybe even detect these EFT parameters, they're called in this context EFT parameters, if you could increase your constraining power here at late times.
Wait, Michael, sorry, I have a question. Is there any reason why these Planck? Oh, it's because of the BAO that the constraints are like very strong at late redshifts as compared to say high, say at 0.1 versus 1000, right?
Mm-hmm. Right. So we get we get the strongest constraints actually at the present time in this specific scenario where we set them all to be equal to each other, because there the constraints are driven by the CMB lensing. I will get to the physics in a second, and then it hopefully will get clear why the constraining power here is different than it is in the early universe, and why about 10 to the minus 3 early and about 10 to the minus 6 late. And before I get to this, here's just a kind of review, and I will just show it to you rather than go into any details because I'm running out of time. So there's a lot of actual particle physics scenarios that you can connect, at least approximately, to this GDM scenario. Like this freely streaming warm dark matter I just showed you, or self-interacting dark matter, or dark matter is coupled to some kind of dark radiation. And you can treat these two ingredients as one generalized dark matter, approximately at least. Then there's fields like axions that have a sound speed that scales like k², for instance. Then I have already told you that this effective field theory of large scale structure predicts a GDM type energy momentum tensor. Then there's more esoteric models like k-essence or constraint norm scalar field theories. And then of course there's also the good old imperfect fluid energy momentum tensor, the Landau-Lifshitz one. And even there you can see in what circumstances you will find a GDM type for these quantities entering the Landau-Lifshitz tensor, energy momentum tensor. So you can find all of these references, not this one, because it was somewhat younger, and it might, so Manuel has written a paper that seems to be connected to the physics that we have, potentially connected to the physics that we have found with this 26 parameter model. So it will be interesting to discuss later.
Yeah, it's a lot of fun.
And now I will quickly, unfortunately, I have to be really quick, show you how the physics of the CMB is actually modified by these parameters. In some sense, it's very, very simple. This W equation of state modifies how this abundance of dark matter scales. And that already tells you there's a, so this is for small w, Taylor expanded. And that already tells you that there will be some degeneracy between the present day abundance of dark matter and its equation of state, because you can compensate one with the other to achieve some early universe abundance. If you say the data wanted a very specific early universe abundance, but doesn't care much about the present day abundance, you would expect these to be very degenerate in the present day and conspire to produce some tightly constrained quantity of the abundance early on. And that's precisely what the CMB tells us. Secondly, the sound speed and viscosity during matter domination have very similar effects on the dynamics of dark matter, and therefore also on the gravitational potential. It induces a decay of the gravitational potential, a gene scale. It's not necessarily an oscillatory behavior that depends on the relative size of these sound speed and viscosity. If the viscosity becomes too big, bigger than the sound speed, there will be no oscillations, and it will just be some kind of damping, what you would expect, for instance, for free streaming when these parameters are freely streaming dark matter, when these parameters are approximately equal. All right, so this is sort of the most important physics that these parameters induce. There's of course plenty of other, and it would be impossible to really find out all the details, but at least this gives you some intuition. So there's a very busy slide that shows you the impact on W, varying W on the CMB. So you see a positive value and a negative value and zero. Zero is the lambda CDM. You see that if you increase W, you reduce the first peak and the second peak and so on. So you, and also the relative peak height of the peaks. And the reason for this is that you are affecting, and here we kept omega, the abundance of dark matter, fixed when I made this plot. You can compensate these two. That's the reason for this degeneracy between W and the abundance of dark matter. So this degeneracy direction corresponds to your ability to move back the peaks to where they want to be. But if you fix omega, increasing W will increase the abundance of dark matter in the early universe, and then you have a different ratio of radiation to matter during recombination, and that's affecting your peak heights. The physics is called radiation driving. And so the more radiation you have around shortly before recombination, the more you boost these peaks. So if you reduce the abundance of dark matter, like here with the negative W, you increase the peaks. It has, here I show you the power spectrum. In changing W has basically no impact on the shape of the matter power spectrum, only gives a slight offset, which is also related to changing matter radiation equality, which can be compensated by adjusting omega. So it has a very, in some sense, boring effect. And it also has no, it's not correlated with the sound speeds. And that will go away if we don't assume the constancy of these parameters. Now, I forgot to mention here the numbers that we get for constant parameters. So it's the 10 to the minus 3. And these numbers, W between plus minus 10 to minus 3, about is precisely because of the CMB forcing a very specific abundance of dark matter around the time of recombination. So that's why, how this number arises.
Sorry, this is maybe a stupid question. So I understand you're trying to do like a changing like one parameter at a time, but from like a more like but I would think usually for reasonable model, these parameters all correlated.
Of course, yeah.
Yes. So maybe the question is that like like when they're correlated, or like could you understand? So when they're correlated, would all this whatever we find change, so will be something new? Will there be something new, like if we do the CMB?
Right. So even though they are correlated, that's the reason why this ellipse is so elongated. It's still not infinitely long. So there's still, even though this direction is much tighter constrained here, and if you marginalize, you get these numbers 10 to minus 3. So the extent here of this ellipse is really what the new physics is you get by introducing this W. And you cannot really get away with it with these correlations. The correlations are, of course, making it more difficult to constrain W, but there is still enough information in there to actually constrain it. And you're right. It's a little bit cheating to just show you what happens if I only adjust W and keep omega fixed. But this is really just to show you what the main physics is, and they cannot exactly compensate. Otherwise, of course, we wouldn't get any constraint on them.
Sure. Okay.
You're
Thanks.
right. Now for the perturbative parameters, they are in some sense much better constrained. So they are about 10 to the minus 6. And the reason for this is how they affect the peaks of the higher peaks of the CMB due to gravitational lensing. So I told you there's this decay scale below which here you see the potential decaying over time in a different way than it does for CDM. Well, the reason for this decay is lambda, and here you see it decays already earlier, this gravitational potential. And that impacts the power spectrum in this way. And if you damp the power spectrum on small scales, you have less gravitational lensing of the CMB. That means that the peaks of the CMB are more pronounced. Here, amplified the residuals with respect to LambdaCDM, so you can see this boost, but it's really what the data is sensitive to. Right, and we also have the degeneracy with the sum of the neutrino masses, which is expected because neutrinos that have mass are approximately modeled by a GDM fluid. So it's expected that we have a degeneracy there. What we have also done is to construct a halo model for this GDM that allowed us to see whether there was, how robust these constraints for the sound speed are, because they come from late time clustering. And so it would be a shame if any nonlinear physics would actually invalidate our constraints. And so we try to find out. It's of course just a very rough way of finding out, but at least we found that our constraints weren't impacted by switching on or off this GDM Halo model. So in that sense, these constraints are robust. Now I'm quickly showing you some results of this Halo model. So you see the power spectrum as a function of scale, and for some parameter, the upper limit. For the sound speed, you see these little wiggles here in the linear power spectrum, no wiggles for the case when there's only viscosity. And now if you switch on the Halo model, you see it bends up, and all the difference basically goes away. So it's in some sense washing out the nonlinear physics, the difference between sound speed and viscosity. But most importantly, our constraints that we found previously without any nonlinear modeling seem to be robust. Now that we have the Halo model, we can also see what happens if we include some matter power spectrum data in the fit. And so we get from the red contours, which are about this 10 to the minus 6-ish, to 10 to the minus 7 in the case where we include not 10 to the minus 7, what is this, 0.5 times 10 to the minus 7, 5 times 10 to the minus 7, sorry. When we include the matter power spectrum with some very conservative cut for the smallest scales to include. So you see constraints improve if you include matter power spectrum data, but it's dangerous because we are now impacted by nonlinear physics, which we don't know much about, especially for generalized dark matter. Now, if you zoom into this thing here, into this corner, you find that if you increase the nodes included in your fit to 0.3, you get actually deviating contours depending on whether you use linear perturbation theory in blue or include the Halo model in orange. So if you would trust the orange model, you would say you have detected non-zero GDM parameters. Of course, we don't trust it, so we don't claim anything like this, but it shows the potential in principle that lies in these matter power spectrum data if we were just capable enough to model it correctly. I will skip over this. This is the expected degeneracy with neutrino mass in this three-dimensional posterior space. I'm soon running out of time, so I will now show you the constraints on W that I've promised you earlier. So this is the boring plot when we assume W to be constant. That's why it's now just this constant bar. And it has this width I mentioned before, about 10 to the minus 3. Now, in the first step, we allowed this W to be free in these 8 bins and set the sound speeds to 0. And the black line is what you would expect for CDM. So everything looks perfect for CDM. CDM sits in the constant W GDM model. The constant W GDM model sits in the GDM model that allows it W to vary in these 8 bins. So everything looks nice and uncontroversial. Here, if you include some more data, the BAO. So just for comparison, this is just CMB alone, and now with some BAO data added. And now the big surprise was when we now included the sound speed and also let them vary freely. We move from the blue contour to the yellow one, and the yellow one is barely consistent here with LambdaCDM, or in this bin, not at all. So this is the 2 sigma error bar. So there seems to be some indication that the GDM model wants to be different from CDM suddenly, because we allowed these parameters to be non-zero. And the reason for this is, so first of all, this is how the full result looks like. It's impossible to show you. That's all the correlations between all these parameters. So it was a massive headache to actually find out what was going on. And I will skip over this. I've shown you this already in the beginning. So now I'll jump to the explanation in the final 3 minutes of what's going on, why we see this shift in the W early on, and also in this abundance of dark matter early on. And the reason is that W and sound speed are actually correlated early on, in contrast to what we believed to be true, coming from the intuition of a GDM-dominated universe where they are not correlated. But early on, during radiation domination, there's a way for sound speed and equation of state to compensate each other. So this is the exact solution for small times or large scales that is used to set up the initial condition in the Boltzmann code. And you see that there's room for adjusting what this initial value is depending on sound speed and W in this earliest bin, which is in our case bin number 8. And that's the reason for this degeneracy. And that's also the reason for biasing it towards positive values, because sound speed can only assume positive values because of stability reasons. A sound speed squared can never be negative. And so this degeneracy direction, therefore, can only bias the W to positive values. And if the W is biased towards positive values, so will be the density, the background density or average density of dark matter. So this is all a very complicated interplay, and is the reason for this shift in early universe abundance. So here you see our succession of papers. It all looked very consistent with LambdaCDM. Suddenly it was shifted to this higher value. And that is explained by this degeneracy in the initial condition. So this just shows you the dynamics. I will skip over this. Apart from pointing out that this degeneracy in the initial condition.
I think we can have like 5 more minutes because we started 5 minutes.
All right, yeah. Okay, then
if somebody wants to go, have other meetings, they can go. But I think you can talk a little bit.
Okay, great. Yeah, so I will briefly explain to you what happens here in this plot. So this is the dynamics of a single K mode of the extracted from class for a bunch of elements of our chain. So you can think of these lines, they reflect where the posterior peaks. So this is basically the most likely models that are plotted here, or their density reflects the confidence And you see that there's this, if I normalize the dynamics here, which you see up there by the CDM best fit model, there's this spread early on, which is precisely possible because of this dependence on these GDM parameters on this initial value. However, the spread in itself is not the interesting thing. The spread is chosen by the CMB precisely so that it can fall down here around the time of matter radiation equality into this bundle of lines. So what we see here is really very much reflecting what we have observed for the background density, that around the time of matter radiation equality, the background density is most strongly constrained. And the same is true also for the density perturbations. Around the time of matter radiation equality, the behavior and the amplitude of these perturbations is most strongly constrained. And so in order to arrive at this very specific bundle, they need to start out with this very intricate correlation between sound speed and viscosity so that they arrive here. And that now impacts what the background density can do, because even though the sound speed wouldn't affect what the background does, because the sound speed is degenerate with the background equation of state, it impacts also via this connection, the background density. So I would say because there's this degeneracy for the perturbations, and because the sound speed is positive for physical reasons, W gets shifted to larger values, and that impacts what the background energy density does before recombination. So that resolves how including the sound speeds and the viscosity as free parameters can impact what the background wants to be. So it's a very complicated story somehow. It has several steps, and I hope I convince you that we understand why we observe this increased energy density pre-recombination. All right, so this is again a plot that I've shown you. But now I also overplotted the best fit value here in dashed, and you see it's actually doesn't look so dramatic anymore. It's not even within the 99% contours early on. That implies that maybe actually if the data doesn't really want it favor this region in parameter space, and we are seeing some geometric effects that arise from the positivity of this large amount of parameters. The 18 parameters for sound speed and viscosity, they are all constrained to be positive, and this restricts the allowed range of parameter space also for the background density. And so the best fit model might not even lie close to what you would naively assume to be the best fit, which is usually around the peak of your posterior. That's not the case here. So that's why one shouldn't get too excited about it. Also, the improvement of fit here is not very dramatic either. Of course, we have a lot of parameters, and we don't intend to claim that we have a preferred model over LambdaCDM. Our many parameters were just there to see if there's any evidence that maybe the data favors a model different from CDM, and it was never intended to be an actual replacement for CDM. Now, once we have found these tendencies, one could go ahead and maybe construct a more restricted GDM model with maybe 1 or 2 free parameters that could mimic what we see here. And then it might actually be favored by the data. But of course, it's somewhat a posteriori and dubious to do something like this. But it's nevertheless interesting to understand what exactly is the main driving reason for this upwards shift, and if it can be actually connected to interesting physics theories about modifications of CDM. Now, in the last minute, I will go to the H0 tension. So this is a slide I copied from Knox. talk I found online. And you see here a 2-parameter space of H0 and the drag scale, the co-moving drag scale of the sound horizon at decoupling, or when the drag epoch ended, which is about the same as recombination. And you see there's this, the actual tension is in the fact that the CMB, the Bluetooth contour is not only not consistent with the H0 confidence limit, but even if you imagined finding some reason to shift this up, it will then be inconsistent with the BAO data. And so the only way of, so this is exemplified, for instance, here by this second plot where he was color coding what happens if you're only looking at the large and small L, and color coded by the dark matter. And you see you move in a direction that is not helpful in resolving the tension. What you really want is a model that allows you to move into this region in this parameter space. And so it was interesting to see what happens for this GDM model, where all parameters are free, and we indeed move into this direction in which the tension gets resolved. Of course, we are not really there, but just there. But it indicates that there might be some interesting possibility of constructing a GDM model tailored to address the Hubble tension. And we are looking into this, also known with more recent CMB data, because this was what I plot here with 2015 Planck data, and we find a more significant, I would say, significant departure from CDM if we include the 2018 data. So it will be interesting to see what happens to this plot when we included the 2018 data. All right, that's it. I think, yeah, maybe 1 minute of summary. I've shown you that this generalized dark matter has capabilities of approximating a lot of interesting physics and is connected to a lot of actual dark matter models out there that are more complicated than CDM. And so far, until very recently, we haven't seen any indication that these parameters parameterizing the departures of CDM want to be non-zero until now. And so this is very interesting, and it is possibly connected to the tension, the Hubble zero tension. And I again want to point out that you can download and use our codes for the modification of class and also our MCMC sampler. And it also has built in a minimizer and visualization tools to maintain your running chains very efficiently and intuitively. Right, and currently we are, as I mentioned already, we are looking into more up-to-date data and see what we can do with this H0 tension. All right, that's it. Thanks a lot.
Let's thank our speaker. I know it's late, but if there are any questions, you're welcome.
Sorry, can I ask a question? Yeah, sorry. I see you mentioned it, but maybe it's something you guys are thinking right now. I guess like yes, this generalized dark matter is, to me, seems more like a parameterization could cover quite wide range of models. But for instance, but I will, since I probably still want to think a little bit more in terms of models. For instance, like you showed, like for the generalized dark matter, like you actually get in this range, you get actually the dark matter density actually somewhat above the cold dark matter. So I'm just thinking, like, what kind of like models could give you that W and C as CS squared, C viscosity squared that is needed to get in this like upper yellow band.
Right. That's exactly what we try to better understand how this can actually be physically implemented. and there might be actually a connection to one of Manuel's papers that I've cited somewhere over here. I forgot the title of the paper, but maybe he can show it in how it's called. And this model has two components: a dark matter model and a dark radiation model. And these two components, they can, in principle, have an equation of state. When you think of this as a combined fluid that is larger than zero, and this combined fluid will also have then a positive sound speed. And so it's possible, or at least it's imaginable, that something like this, that early on has a positive W and a positive sound speed, and then both of them go away over time, might actually produce something like this.
Okay, thanks.
Yeah, like that's what I was thinking, that the earlier part, right, that seems to shoot up, that seems to indicate like a higher W than zero. And I think you had shown us, it didn't reach 1/3, which is what happens for radiation. But
Right.
it was definitely, right, it was like 0.1, point-ish, something like that. That's interesting.
Yeah, and the thing is, if you think of this as a kind of effective description of a combination of dark matter and dark radiation, you wouldn't expect it to be 1/3. You would expect it to be something bigger than zero at least. And so this is what we find in these first two bins.
Yeah, that's right. And yeah, right. Yeah, okay. I have a question myself. In like the next slide, when you talk about delta hat, you have some plots with like the rainbow there. So again, this delta hat thing is what gives you the non-adiabatic pressure, right?
Okay, I think I just plotted delta hat here because I've implemented the class or this modification to output this gauge invariant co-moving density perturbation. But if you would plot the synchronous gauge density perturbation, it wouldn't really look much different, because I might actually have, let me see, somewhere in my backup slide some formula. Right. So this is this delta hat. So it just contains, in addition, this velocity perturbation, and this usually doesn't really impact much the amplitude of this density. Basically, for CDM, this just disappears because the velocity perturbation can be set to zero.
Right.
And so
but if I remember correctly, this guy goes into the calculation of your capital pi, right? Like the perturbation of
this guy, yes.
Yeah.
So the capital pi is proportional to CA squared minus CS squared, or the other way around, CS squared minus CA squared times this.
Right. So the fact that all of these lines converge at equality seems to say that we want whatever non-adiabatic part there might be to be the same as in CDM, right? But the rest of all of them converging, this delta hat has to be the same as delta hat from CDM. Seems to say, okay, at this point, we want the pressure to look the same for both models, GDM and CDM, but everywhere else, in fact, seems to be preferred some other kind of pressure behavior. Do we know why there's this convergence, or is it? I mean, I know that's a kind of a hard question, but
yeah. So the thing is, the pressure is actually not really. Honestly, I think I might have never plotted similar lines for the pressure, but it's not. It's not that this non-adiabatic pressure is, I think, the crucial part here. I should actually check it out. So I think it just, the CMB just cares about the dark matter density perturbations, because after matter radiation equality, they source dominantly the gravitational potential, and the relative peak heights in the CMB, they know about then the actual dark matter perturbation amplitude at this particular time, and the Poisson equation is sourced by this guy, actually by this delta hat. So in that sense, it's also natural to plot this delta hat because you know it's proportional to the gravitational potential.
Right,
when
Sachs-Wolfe comes in, yeah.
Yeah, so I would say the CMB likes it to be bundled here because the potential is predominantly sourced at this time, or starts to be sourced at this time by the dark matter alone, from this time onwards at least. So whatever happens here is crucial for the gravitational potential at recombination.
I see, thank you.
Any other questions? I have one myself. If you go to the first plot you showed, how it solves the sigma 8 and H naught.
I mean, solving is maybe too much. It's
the color is with the equation of state today, right?
Yes.
But you said,
I think I just chose it because it was one interesting choice that would produce a nice gradient. There might be other interesting.
Is that within the limits of the error bars at today? Because I think you said it to be 0 at late times because it degenerated with lambda.
No, we don't set it to 0. We have the bin, the very final bin for W twice as big as for sound speed and viscosity, because it is degenerate with lambda, but we never set it to 0. So so you can read off the 0 sub part would be around here.
Okay.
The green colored.
From that, you can see that in order to completely solve the problem, you will need something that's quite warm, about 0.1 today, which how about structure formation? Could that kill that possibility? I mean, from galaxy service?
So this is also, I think, reflected here. The higher the abundance of dark matter is, the more you move towards this direction.
Yeah, but about galaxy service, etc., could that put constraints and not allow that value to be that high today?
Yeah, I don't think that galaxy surveys, as far as they depend on early universe physics, the imprint of this Drake scale, they only are sensitive to this ratio of angular diameter distance and this intrinsic Drake scale. So if you are capable, say, with the W, some funny W behavior in the late universe, to fudge together a angular diameter distance that would be even smaller, then you could maybe move up here. So it's really this GDM model allows you enough flexibility to toy with, or in this case, we of course didn't toy manually. It was what the data favored, but it allows you to adjust what happens pre-recombination, fixing this Drake scale. But it also allows you to modify all the dynamics and background, in this case, particularly for the to change the angular diameter distance so that the peak position is still at 1 degree. So that's, I think, the crucial thing. And when you make sure that the angular diameter distance to the Drake scale is right, then also your galaxy survey is probably going to be fine.
Okay, thank you. Any other questions? Okay, let's thank our speaker again. And